All right, in this video, I'm going to continue to look at the chapter section 4.2 addition rule and multiplication rule. So last time we studied addition rule, right? And then I just briefly introduced the multiplication rule here. So probability of A and B. So it means that probability the event A occurred and event B occurred, right? So first trier and second trier respectively. So that can be that probability we can find that we can find the probability that A and B using that formula. Probability of A times probability of B bar A that is called conditional probability, which will be covered in section 4.3. So that today I'm going to cover the multiplication rule, which is in second part of section 4.2, and then 4.3. Okay, so P of B bar A means the probability of B given that event A already occurred. Okay, so then the so to apply this formula into the problem, we have to um, study the independent and the with replacement and the without replacement, those terminologies first. So look at the independent. A and B are independent. It means that the occurrence of one does not affect the probability of occurrence of the other. So it means that, for example, event A and B are independent means that probability that event B will be B is occur will not be affected by the probability of event A occurred. Okay, so it means that then the conditional probability that B will be occurred given that probability A is already occurred is equal to probability of B, just because the assumptions event A is already occurred will not affect the probability of B. Okay, so here's the example: 25% of NGU students are commuters. Would commuter and eye color be independent? Yeah. So the probability, for example, student's eye color is brown, you know, it's not, it does not affect the probability that the student is commuter. Okay, so and the commuter and the age be independent. Yes, it was independent. Okay, and the what next one is a replace without replacement. This is really important. Listen carefully. So when sampling with a replacement, selections are independent. With a replacement means that here. So for example, you there is a candy jar. Okay, so maybe five blue candy and then 10 red candies. So you select the one candy, and the probability that this, the color of the candy you selected, you picked, is blue gonna be 5/10, right? But then we just picked one candy, and then you pick the second candy, and then probability that the the second candy with blue color of the second candy, okay, you picked, is blue. That probably gonna be will be, you know will depends on what depends on the you put whether or not you put the first candy you picked, put it back to candy jar or just leave it. Okay, so that totally depends on. So if you want to, you just pick the first candy and then look at the color and then put it back. That's the with replacement. But once you just pick the first candy and then the you don't put that back into jar, that means without replacement. So think of this first case. You just you pick the first candy and then put it back into the candy jar, and then you choose the second candy, and then probability that the color of the second candy is blue gonna be still 5/10, which is one half, right? But what if you just didn't put the first candy back into the candy jar? Okay, then what? The probability the second candy, the color of second candy is blue will depends on the color of the first candy, right? So now, when sampling with the replacement, the selections are independent. So the color of the second candy and the color of first candy will not be affected each other. Okay, so probability don't change. Yes, the when sampling without replacement, then selection is dependent. So probability change. So without replacement, you have to apply. You have to apply the conditional probability, and then with this replacement, then two events are independent. So conditional probability becomes just regular probability like this. Okay. Now, 5% guideline. When small samples are drawn from large populations, sample is no more than 5% of population, you may treat dependent events as if they are independent because it is rare to select the same item twice. Yes, the answer will be close, but not exact, but approximately it means. So I'm going to talk about this one later too, okay? So first one, let's see. Um, this example, relating to multiplication rule and then replacement without replacement. Okay, so if two test subjects are randomly selected, so we can use classical probability. Okay, that approach. Find the probability they both got first positive test result with replacement without replacement. So then the both got first positive test result, right? So that means, let's say probability A is the set of positive test result. Okay, and then B is also the set event V is the set of all the person who had positive test result. Okay, then we're gonna find the probability of A and B, right? Okay, because the problem says that find the probability they both got first positive test result. So okay, so now then this is gonna be P of A, right, times the probability of B bar A, is it? Okay, but since you said with replacement, so then what? Then conditional probability going to be equal to what? Probability of B. So this is equal to P of A times P of B. Okay. So what's the probability A? That means the probability that we choose the person who had a positive test result, 134 over 1,000, right? So 134 divided by 1,000. Okay, and then times, and then what's the conditional probability that we choose a person, which is in second we choose the person given that we choose the positive test result. We choose the person who had a positive test result in the first. So that's going to be what if replacement is not the occur, okay, without replacement. What I mean, then the probability going to be one, not 134, 133, because we already choose the person who had a positive result in first. So that, and then without replacement, so we don't put the that screen test, put it back. Okay, so total number of the person who had positive test result will be reduced by 133. 133, right? And then over how many now? How many the outcomes left out of what? Because we picked the one screening test, right? And then we don't put that screening test back to the kind of in the sample space. So total number of sample space reduced by 999. So it's going to be 133 over 999. Okay, so that's going to be a conditional probability without replacement. But here, you see that here with replacement. So then what? P B bar A is nothing but P of B, because once you check the test result, once you just once we pick the first screen test, and then we look at the test result and then put it back, right? So the probability that we choose a screen test had a positive showing the positive test result is going to be 134 over 1,000, even even event A already occurred. Okay, So now what about this? Without replacement, okay, then PA, probably A and B is equal to P of A times P of B bar A. So we only calculate conditional probability, okay? So without replacement, then event A and B are not independent, okay? So not independent, independent. It means that event A occurred that will affect what if probability that B occurred, okay? This is gonna be 134 over 1000 times, okay, and then 133 divided by 9999, okay? So now next one, if 3 test subjects are randomly selected, then find the probability all 3 got first negative test result. So with the replacement, yeah, similar to this, okay? So now this one gonna be what? P of A and B, okay? I mean, so let's see, P, A, and B, and C. Okay, so A represent the we uh uh we had a positive negative first negative test result at first, and the B, what the first the probability of event B is the set all the outcomes having the first negative test result and second, okay, second choose, okay, C is the third choose, okay. So now let me see, what's the first, we need to figure out the first negative test result. So here, so we already figured out first negative type test result, first positive. This is the first, right? First negative test result. Why? Because you see that the this 6 person did well use the draw, but in a screen test, result is what? The negative test result. So that's the first negative test result, and then 90, that's the first positive test result. First positive test result. Okay, this is going to be then, so with the replacement, so since replacement is allowed, so the probability that we choose the first negative test result out of 1000, the screen test is what, 6 over 1000, right? And then once we check the test result, and then we put that test test sheet into back, right? So now it means that what, the probability that we choose in the second trial, the probability that we choose the first negative test result is going to be still 6 over 1000. Okay. And the third trial, same. Okay. And without replacement, then probability that A and B and C is going to be, since replacement is not allowed. So in the first trial, probability that we choose first negative test result is going to be 6 over 1000. And then second trial, since the total number of the first negative test result outcomes is reduced by 5, right? And then total number of outcomes is also reduced to 999. And third trial is going to be 4 over 998. Okay. So see that with replacement, without replacement is really important. Okay. With replacement means that two outcomes are independent. Key mind is mutually exclusive independence are totally different. Mutually exclusive means that two outcome doesn't have a common outcome. It means that P of A and B equals 0. Okay, it's called disjoint. Okay, so and then independent means that the probability that probability that the event A occur will not be doesn't affect the probability that the event B occur. Okay, so keep in mind this. So the mutually exclusive is related to the addition rule, and the independence is related to the multiplication rule. Okay, keep in mind this. So now next problems. Example. So acceptance sampling on among the 810 New York airport baggage scale, 1 or 2 are defective. So if 4 randomly selected scale are tested, and then what is the probability that all four are okay? Thus, causing the inspector to believe all of the scales are okay and upsetting them. So then, you can consider that the first we for trial will be the applied, right? So choose one baggage and then check the whether or not that baggage scale baggage is if defective or not. Okay, and then the second trial we pick the second we pick the other baggage. Okay, and to check that that package is defective or not, right? So we want to find the probability that N, B, N, C, N, D. So here ABC event ABCD means that what the event that the baggage you know or suitcases are okay, not defective. Okay, so that is equal to. So now you see, then replacement is allowed or not allowed. In common sense, replace should not be allowed, right? Right. So now, then what? The all events must be not event independent. Okay. Then probability. So it means that the what? For second trial, probably the event B occur will be, you know, affected by what? Event A already occurred, right? So and then probably that the event D occur will be affected by what? Event A and B and C already occur, right? So those four events are not independent. Keep in mind that. So now then, let's find out P of A. Probability A occurred is going to be what? So 102. I mean, what? 810 minus 102. Okay, give me a second. 810 minus 102, which is the 7 or 8, right? So 7 or 8, these are that number 7 or 8. This is a number of the suitcases are not defective. So, I mean, which means that these suitcases are okay, right? So okay, yeah, not suitcase but baggage scale. Sorry, I was confused. So now then, it's gonna be 708 divided by what? 810. Okay, so 708 is a number of the baggage scales. Okay, uh, that are okay. Okay, so that's a probability of A, P of A, and the times. The second trial, probability that the second selected baggage scale is okay. The probably gonna be what? 707, because event A is already occurred. It means that we already selected what? The one baggage scale which is okay in the first trial. So number of the baggage scale which are okay is reduced by 707 over 809, because total number of baggage scales also is reduced. So times, and then 706 times 808, third trial, and then last trial going to be 705 times 807. Okay, so now next one example. Okay, redundancy. 2% of computer hard disk drive fail each year. If you have a single hard disk drive in your computers, what is the probability that it fails in a year? So let's see. Then in this case, what? The probability is already given, right? 2% of computer hard disk drive fail each year. So the probability going to be 2%, which means 0.02, right? Okay. And then you have only one hard disk drive, so it means that what? Probability that we'll deal with only one single event. That event is what? Event means that the single hard disk drive in your computer is failed. Okay, in a year. So that's going to be 0.02, right? So this case A is the what? The single hard disk drive is in here. Okay, so the P of A is equal to 0.02. What about this? If you also have a second independent backup disk in, okay, so what's the probability that they both fail in a year? See the independent, right? Okay, so that means what? P of A, it means that probably the second hard disk drive fail will not be affected by probably the first drive hard disk drive fail in a year. So then A is the one set of the first hard disk drive. Let's say HDD. Okay, here. Okay, and then B is, let's say, the second hard disk drive fails in a year. Now then, probably the what? B, you see they both fail in a year. Probably A and B, right? This is equal to. Well, so then two P of A. The formula multiplication rule is this: P of A times P of B bar A, right? But since what? Since two events are independent, right? See that second independent. You see, so this is equal to P of A times what? P of B. Now that is going to be what? 0.02 times 0.02. Okay. So if you have a three independent hard disk drive in your computer, so what's probably probably all three fails in a year. That's going to be 0.02 times 0.02 times 0.02. Okay. Then a couple has three children. Find the probability that exactly one of children is a boy. So in this, okay. So is that? I mean, let's say event A is the first child is a boy. The event B. What's the question? Is this: find the probability that exactly one of the children is a boy. Okay. So then we can think about this. Not first, sorry. A child out of three children, boy. Okay. Then let's figure out the sample space. Okay. Then let's say B means boy and the G means girl. Then we can say starting from BBB. Okay, and the BBG and then BG. We haven't seen this one, right? BGB and then what? GBB, right? And then BGG, right? And then GBG, then GGB, and then GGG, right? Okay. So we have 8 outcomes. These are simple event, cannot be broken down further, right? So 1, 2, 3, 4, 5, 6, 7, 8. Yes, right. Now then, or yeah, okay. So now, then probably A will be. Let's figure out the outcomes, okay? In event A, it's gonna be what? Just event A is what? We're gonna find the outcomes in a sample space having only one boy, okay? So it's gonna be just a BGB. See, yeah. So now BGG, and then it should be B, right? GBG, and then GGB, right? Excuse me. So these outcomes have only one boy, right? One boy, two girl, right? So this is probably A gonna be N of A, applying the classical probability. Classical probability gonna be what? P of A gonna be number of outcomes. Event A divided by number of outcomes in sample space. So N of S, which is what? 3 over A. Okay. So and then you definitely you have to convert that fraction to the decimal place, showing up to 3 significant digit. Okay, so now the example, a couple has 8 children, and then find the probability that exactly one of the children is a boy. So now then, I mean, these look at these two problems. What's two? You may wonder that okay, two examples are related to the multiplication rule. Yes, because give me a second. See, because here before solving the second example, look at this. We can say let's see. Okay, give me a second. See, give me a second. So we can consider this. We can the find the we can figure out that probability by applying the multiplication rule. How come? Because look at this. Let's say A is the first child is a boy, and the B is the second child is a girl. C, the third child is a girl. Okay. And then we find that probably A and B and C. But we know that what each event all three events A, B, C must be independent. Why? Because the probability that second child is a girl will not be affected by probability the first child is a boy. And then probability that the third child is a girl will not be affected by the second child is a girl and the first child is a boy. So all three events are independent. So this is equal to what? P of A times P of B times P of B times P of C, right? Okay, so that is equal to actually what? So half times half times half, is it? So which is 1/8. Now, so that's not the answer, okay? So we can think about this. First child is a girl, and the second child is a boy, and then third child is a girl. Still one, that probably going to be 1/8. And then for second child, the first and second children are a girl, and the third child is a boy. That's probably going to be 1/8. So 1/8 plus 1/8 plus 1/8, which is 3/8, which is exactly the same as that number, right? Okay, that's the other way to find out the that probability applying the multiplication rule. Okay, so but which one is easier than the other one? I think this is easier than that one, right? Okay, so now a couple has 8 children. Find the probability exactly one of the children is a boy. Okay, so now then what? Then we find out what? Let me see. Probability A is equal to a child is a boy. Because couple has 8 children, so it's hard to list all the possible outcomes, right? And it belongs to event A, right? So then in this case, if the number of children, you see number of outcomes, I mean number of combinations is getting complicated here, then we're gonna use that method, what we did. Okay. So first we'll find out what P of A probability that A and B and through the what, H, right? To H, because 8, 8 events. Isn't it right? Yeah, right. So now that's gonna be P of A, right, times through the P of H. Okay. So what's it here? Let's say A is the event A represent the first child is a boy, and the all other in the event B through H are events that the children is a girl. It's gonna be what? One half times actually one half to the eighth power, right? Is it? Now then now we're gonna what? Think about the other cases. Event B is the is to represent the first child is a boy, and all other events represent the child is a girl. Doing this, then we're gonna get this: A times probability that exactly one of the children is a boy will be what? A times 1/2 to the a's power. Okay. So now, and then just using calculator to figure out decimal expression of this, and then round up. Okay. So now summary: P, A, or B is added, but don't count anything twice. Okay, using the addition rule. Okay. P, A, and B multiply, but be sure P or B takes A into account. Yeah, keep in mind this. All right, now, so we have let me see. Yeah, let me go over these problems. Let's see. The next time, okay, and then let me go over the NNIST, okay, to figure out the probably the NNIST one occurrence of A is one. I explained about this one roughly, and just take a look at this one, okay. So to do that, we need to see this one, study this one, rule of complementary event. So let's see. Let's look at the lecture slide. We use A bar to indicate that event A does not occur. So common sense dictates this principle. We are certain with probability 1 that either an event A occurs or it does not occur. So it follows that P of A or A bar must be 1, right? Okay. So for example, okay, so um what? Give me a second. So when you're just tossing a coin, then let's say event A represent the you got head. Okay, when you're just tossing a coin, then A bar means that what? A bar, the event A bar means that you get the not head but tail, right? So probability that A or A bar means the probability that you get a head or tail. What's the probability that you get A or tail? Is there any other options? No, right? You should get head or tail when you're tossing a coin one time, right? So probability that A or A bar must be 1. It makes sense, right? Because events A and A bar must be disjoint. Disjoint means mutually exclusive. It means that there is no common outcome between A and A bar. It makes sense. Right? So we can use the addition rule to express this principle as follow: P A or A bar is equal to P A plus P A bar, which one, right? Now then, look at this: P A plus P of A bar equals 1. Here we're gonna isolate P of A. Then we're going to get this. We see that P of A is equal to 1 minus P of A bar, right? So that's what we saw in the last time, right? So this is called the complement a rule of complementary rule event, okay? Or we can say P of A bar equals P or 1 minus P of A, okay? So now, excuse me. So P of and this the one occurrence of A is equal to P 1 minus P of no occurrences of A. Yep, now that makes sense. And this the one occurrence of A. It means that and this means that one or more, right? So occurrence. Then we're gonna subtract the probability that no occurrences A from 1. Okay. Now look at the example. Excuse me. A couple has 3 children and find the probability that they have at least one boy. They're gonna find this. Let's say A is equal to, so 3 children and least one boy. Then all, let's see. Then you can say B what? Find the sample space first. Okay, sample space is gonna be BBB and the BBJ and the BGB and then GBB and the BGJ and then GBJ, right? And the GGB and the GGJ. Yeah. So now then, let's see. How many outcomes has at least one boy? So all of outcomes except for GGG, these outcomes have at least one boy, right? So now then, they're probably gonna be what? 7 over 8, right? But let me use a rule of complementary event. Then let's say A is the at least one boy, okay? Then P of A bar, let me use a prime, okay? A prime, A bar. Sometimes textbook use A prime, some textbook use A bar, okay? So it means A bar, A prime, okay? So for convenience, so A prime, oh, then P of A, sorry, this is equal to 1 minus P of A prime. Okay, so now this is equal to, think of this, P of A prime is what? Probability that, you know, no boy in 3 children, right? That's the A prime, right? So this is going to be A1 minus what? 1 over 8, is it? Because how many outcomes have, has no boy? See, only one outcome, G, G, G. This outcome has no boy. So how many? So 1 out of 8. So 1 over 8, that's a P of A prime. Okay, so that's going to be 7 over 8. Okay. Example, the next example, 12.4% of the burglaries are cleared with arrest. Out of 5, the burglaries, find the probability that at least one is cleared. So at least one is cleared. Whenever you see that at least in the problem, you gotta use rule of complementary event. Okay. So now P of, let's say A is the what? At least the A is event A is the set of all the outcomes. Showing that at least the one is cleared. Okay, so here at least one is cleared. Then we're gonna find out P of A using rule of complementary. Okay, so 1 minus P of A prime. So what's the A prime? A prime is that what? Um, no burglary is cleared. Is cleared. Okay, so then 1 minus. So all burglaries are not clear. Okay, so that means what? It's going to be 100% minus 12.4% because 12.4% of burglaries are cleared with the arrest, right? Okay, then so there's going to be 87.6%, right? So 87.6%. So that's the probability, because keep in mind is all percentage means the probability. Okay, so this is probability that what the the randomly selected of the burglary is cleared with the arrest. Okay, so that means 87.6%. That's a probability that randomly selected the burglary is um, not cleared. Okay, uncleared. Okay, with arrest. So 87.6% to the, because out of 5 burglary, right? So to the we're gonna multiply 87.6% 5 times. So which means that 87.6% to the 5th power. Okay, then we subtract that number from 1. Okay, so then using calculator, we got the point 484. 484. Okay. So now, next example, 12.4% of burglaries are cleared with arrest. Out of 5 burglaries, find the probability that all 5 are cleared. Okay, all 5 are cleared. Then you don't have to use the I don't think you gotta use the rule of complementary event in this example. So just all 5 are cleared. That means what? 5 are cleared. Let's say the event A consists of all the outcomes um, represent the all 5 are cleared. Actually, we can see only one outcomes, right? Event A has only one outcome. Okay, so then P of A is going to be what? Just 12.4%. I mean, to diffuse power. Okay, so the key one is when you compute this one, you have to convert the percent to the decimal number. Okay, so 12.4% means what? 0.124. So this is equal to 0.124 to diffuse power. And when you calculate using your calculator, you may get this kind of number with a letter e minus 5. So e minus 5 means that 10 to the negative 5. Okay, so that expression is nothing but 2.93162. Okay, 5062 times 10 to the negative 5. Okay, so 10 to the negative 5 is what? Point 0.00001, right? Okay, so this is equal to then what? Point. Give me a second. Complicate. Yeah, that's going to be 0.000, and then one more 0 and the 2. Okay, 9316. I think 9293. That's enough. Okay, 3 significant digit. Okay. So now conditional probability. Let me cover conditional probability next time. Okay. So we learned the multiplication rule and the with replacement, without replacement, and then complement rule of complementary. Okay, and then so I'll just go over these problems next class, and then I'm gonna go over the conditional problem next time. Okay, let me stop here.